Yeah, here we have the first one. Explain what is meant by the diffracted waves. So, not a tricky one. The waves which are bent around the corners of the obstacle or around the corners of the slit, those waves are known as diffracted waves. If the phase difference between two waves is uniform or constant, then the two waves are said to be coherent waves. Only if the if the phase difference between two waves is uniform. But let's move on to the next one, which is the mathematical and slightly tricky. I won't say tricky, but slightly different. Light consists of two wavelengths, lambda 1 and lambda 2 is incident normally on a diffraction grating. Okay. The third order diffraction maximum of wavelength lambda 1 and the fourth order diffraction maximum of the wavelength lambda 2 are at the same angle theta to the direction of the incident light. So this is something that joins the two waves. The angle of diffraction, they are saying they are diffracted at the same angle. The angle is same. So let me write down the expression from the first sentence. The third order maxima with wavelength lambda 1. Third order maxima with wavelength lambda 1. So the expression would be n lambda equals to d sine theta. This is the general formula. For third order maxima, 3 times wavelength is lambda 1 equals to d sine theta. Diffraction grating is same. So we don't need to add the subscript with d because we have the same grating. Now for the next one here. And the fourth order diffraction maximum of intensity of the light of wavelength lambda 2. What does that mean? Let us write the expression for that one. Fourth order diffraction for wavelength is lambda 2 equals to diffraction grating is same. D would remain without its subscript, sine angle as it is because the angle is also same. Now the first thing equals to d sine theta. The second equation for lambda 2 equals to d sine theta. If both of them are equal to d sine theta, then that means they are also equal to each other. And then we have the next one, the coherent waves. We need to find the ratio lambda 2 over lambda 1. So I'll keep lambda 2 on the right side and I'll bring lambda 1 from the left side and it will be divided over here and you'll be left with 3 over 4 and lambda 2 over lambda 1, the ratio you'll be left with 0.75. You can hear it on the calculator. So this is how we solve the first part. The difference between the two wavelengths is 170 nanometers. So 170 into 10 raised power minus 9 with the unit meter. Determine the wavelength lambda 1. So I think we have two variables, but at the same time we have two equations. One of the equation is, I can also rearrange this one as lambda 2 equals to 0.75 times lambda 1. So this is the first equation. All right, here we have the first one. I can simply copy paste over there. Come on, boy, just paste this one over here. Yes. And the other expression I can form from the first statement, which says the difference between the two wavelengths. So what do we have then? Lambda 1 would be written as it is. Instead of lambda 2, you can insert the value, which is 0.75 times lambda 1 equals to everything else as it is. What else do you have? Basically this is 1 lambda 1. 1 lambda 1 minus 0.75 lambda 1. What are you left with? 0.25 lambda 1 equals to 170 into 10 to the power minus 9. And thereby lambda 1 equals to 170 into 10 to the power minus 9. I need someone to do it on the calculator quickly. Divided by 0.25. Now the number should be increased to 4 times. Just multiply 170 by 4. You'll be getting the answer. Okay, 6.8 into 10 to the power minus 7. Alright, 6.8 to 10 to the power minus 7. Oh, but we need to answer in nanometer. So I won't change this thing. I would simply divide 170 by 0.75. So if that was the answer, you'll be getting 680 into 10 to the power minus 9. But this thing, they have added nanometer as it is. So you'll be getting 680. And matter of fact, we were not required to convert nanometer in meters to begin with. We should have kept nanometer in nanometers. We would have been getting the answer right away. Conversion was not needed in this case because the answer is also needed in nanometer. Okay, so you can write it down by yourself. When two or more waves of the same type meet at a point, then the resultant displacement is the sum of their individual displacements. And then we have a question which looks like from the topic of Young double slit experiment, and I can quickly write down the formula of Young double slit experiment. I don't even know if they'll ask me to use the formula, but I'll just write it anyway. What does A represent? A is over here, which is unknown. Okay, A is unknown. Lambda is given 610 nanometer. The value of D is 2.7 meters. The value of X, we can always find the value of X indirectly here. So basically what we have is, this is a central bright fringe. Okay, I'll try to label the bright with the highlighted one. Let's go this way. This is a bright fringe, and then 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 this is a bright fringe. So this one is the central bright fringe. Which is n equals to 0. And this is the point, these are the points where the first destructive interference takes place, and the first destructive interference takes place at n equals to 0.5. The second destructive interference takes place at n equals to 1.5. The third destructive interference takes place at n equals to 2.5. Then 3.5. But the first constructive interference takes place at n equals to 0. And then the following constructive interference takes place at n equals to 1. So you get a bright spot there. And then the next one takes place at n equals to 2. So you get a bright spot over there, once again, at the top, at the bottom. So this is a situation that we have. And thereby we can find the value of X, which is the distance between any two consecutive, either you can say bright fringes or dark fringes. So distance between the first two, distance between the second two, distance between 3 bright fringes, distance between 4 bright fringes. So 22 millimeters is distance between 4 bright fringes. Hence, the distance between 2 bright fringes would be 22 divided by 4. But what is the point? Let's get back to the question. What is the point P? Point P is where the value of n is 1.5. Where second time the destructive interference takes place. So we use the formula of the path difference. Path difference equals to n lambda. And the value of n over there is 1.5. Because this is the second destructive interference. You need to Remember this, at the first destructive interference, value of n is 0.5. At the second destructive interference, value of n is 1.5, and so on. So 1.5 times, do we have the value of the wavelength? Now we gotta find the wavelength also. 610, okay, 610. We need to determine the value of x. So for this one, I'm going to write down the formula straight away. Lambda equals to ax over d. I can rearrange a equals to lambda times d divided by x, and then a equals to lambda was, let us insert the values in this one. Lambda was 610. Yeah, this time we need to answer in meters. So 610 into 10 to the power minus 9, and the value of x was 5.5 millimeters, so 10 to the power minus 3, and d is slit to screen distance is 2.7. So can someone write it on the calculator? Okay, 2.99. Okay, 2.99 into 10 to the power minus 4. All right. You can also write in 2SF. In 2SF, it would be 3.0 into 10 to the power minus 4. That is also, both of these are acceptable. A higher frequency of the visible light is now used, so they have changed the color. Now probably, let's say the initial one was red, now they have used blue. If they have, let's say, increased the frequency, it could be anything, but let's say they have gone from red to blue. So explain the change to the separation of the fringe. So if they have increased the higher frequency, it means they have lowered the wavelength. So lowering the wavelength, what is the effect on the fringe spacing, which is x? So what formula do we have? Lambda equals to ax over d. What does that mean? If we increase the value of, sorry, if we decrease the value of lambda, the value of x would also decrease. So fringe spacing decreases. But you need to write the entire statement. Higher frequency means the lower wavelength, and hence, according to the formula, lower wavelength means lower wavelength would correspond to less fringe separation. Okay, and let's move on to the next one, which is the intensity of light incident on double slit is now increased without altering the frequency. Compare the appearance of the fringes after this change. Okay, the intensity is now increased. So we study the factors. I mean, the most advanced factor is if you increase or decrease the intensity from one of the slit. But in this case, they have increased or decreased the intensity overall. They have increased the intensity. So what happens to the fringe pattern? First of all, fringe spacing remains same, because in the formula lambda equals to ax over d. X represents the fringe spacing, which is lambda times d divided by a. Hence, the fringe spacing is not affected by the intensity. So fringe spacing remains same. The fringe spacing remains the same. But what happens to the pattern, fringe pattern? If you have increased the intensity, the amplitude of the light would be increased, and now your bright fringes would be brighter. And dark fringes, same. Because at the dark fringes, the pure destructive interference takes place even if you have increased the amplitude. So for example, you have increased the amplitude, Initially, let's say these two were being combined, these two, you have increased the amplitude, and now the two waves, after they pass the wave after they pass through the two slits, look something like this. So initial value, let's assume 2 2. The overall amplitude for the constructive interference would now be 4. Hence, the bright fringe would be brighter because it has the amplitude 4. But for the destructive interference, 2 would combine with -2, and for destructive interference, you'll be getting 0. And with the higher intensity, let's say the amplitude has now increased. Okay, the amplitude has now increased, let's say 3. So 3 once combines with the other one, 3, the overall amplitude would be 6 for constructive interference, but for destructive interference, it would still be 0 because 3 would be cancelled out by -3. Now, depending on the question, we got to be using one of these two formula. And there's another important pointer here. If the path difference is integral multiple of lambda, integral multiple of wavelength, then we get constructive interference. If the path difference is not an integral multiple of lambda, rather it is like 0.5 times lambda, 1.5 times lambda, 2.5 times lambda, then we would be getting destructive interference. Anyway, let's move on to this one. This question is from the topic diffraction grating. The wavelength of the wave is given as 640 nanometer. So I can write it as 640 into 10 to the power minus 9. What else do we have? Incident normally okay on a diffraction grating having a line spacing of 1.7 into 10 to the power minus 6. Luckily, they have given us the value of d straight away. So the distance between two consecutive lines on the slit of the diffraction grating is 1.7 into 10 to the power minus 6. How many orders do we see? The center one, the 0 order, and then the first one, and then the second one. So 2 orders at the top, 2 orders at the bottom, and then we have 1 in the middle. So the value of n, if I could write value of n, this is n equals to 0. This one and this one are collectively n equals to 1. This one and the one at the bottom are collectively n equals to 2. Alright, so in the first one, the second order diffraction maximum of the angle of the light is at the angle theta to the direction of the incident light. Show that the angle theta is 49. And the question is for 3 marks. So I'm going to write down the formula so I can score at least 1 mark straight away. D sine theta equals to n lambda. So let me insert the value of d. And let me find the value of sine theta. You should not be inserting the value of theta. I mean, this is what we are supposed to find. Our final answer should be 49. And then for the second order, the value of n should be 2. And the wavelength was given as, somebody should open up the calculator, 640 to 10 to the power minus 9. So this thing would be shifted on the other side in the denominator. Will look something like this. And then I can take sine inverse of whatever my answer is on the right side. Okay, here we have a text. 48.8. Okay, very good. Yeah, 48.8 into SF, you can round it off to 49 degrees. So this is the answer. It was meant to be shown. You must write down the formula. It gives you C1 compensation mark. And this is for the calculation for the second. The final answer is for the third, A1. Okay, anyway, let's move on to the next one. Determine the different wavelength of visible light that will also produce a diffraction maximum at the angle at an angle 49. All right. So we need to determine a different wavelength that would also produce a diffraction maximum at an angle 49. All right. So we can find the value of lambda. We need to find the value of the new wavelength. So I'll just simply change the value of n, and from n equals to 2, I can increase the value of n to the next uh, order. So n lambda equals to d sine theta. Lambda needs to be found out. So d would be, how much was that? 1.6 into 10 to the power, sorry, 1.7 into 10 to the power minus 6. Now for the new wavelength and for the same angle, we'll change the value of n from 2 to 3. Let's see what do we get. 4.2 into 10 to the power minus 7. I hope you have rounded in 2SF and we get 4.2 into 10 to the power minus 7. So this is a wavelength of a different wavelength of the visible light that would produce a diffraction maximum at the angle 49. Let's move on to the next one. I'm going to skip the definition. I'll define them anyway. For a progressive water wave, state what is meant by the displacement. So probably the easiest one. You don't get definitions easier than that. The distance of a point on a wave from mean position is known as displacement. Distance of a point on a wave from the mean position. Amplitude, the maximum displacement of a point on a wave from the mean position. Maximum displacement. All right, anyway, here we have the next one, which is related to the intensity. So the question says, two coherent waves x and y meet at a point and superpose. Superpose, simple words mean combine, but the key word is superpose, because the two waves have to be of the same kind. They must be having same frequency. The phase difference between the two waves is 180. Okay, this is the phase difference. Means if one wave is at the top, the other one, if one wave is having a crust at the top, then the other wave must be having trough at that point. The wave x has amplitude 1.2 and intensity I. The wave y has amplitude 3.6. Okay. And what we are supposed to find is calculate the intensity in terms of I of the resultant intensity at the meeting point. Okay, we need to find the intensity of the resultant wave in terms of I. I is the intensity of the wave x, by the way. We need to find the intensity of the resultant wave, not a numeric value, but in terms of I. So let us first find, what do you call that, the amplitude of the resultant wave. So let me call this one x2 and I can call this one x1, and the amplitude of the resultant would be the difference of these two, because they have a phase difference of 180. That's why we know that these two waves must be subtracted. Their amplitude must be subtracted because they have a phase difference of 180. So two waves with a phase difference of 180 will look something like this. If one wave is something like this, the other one would be kind of like this. Minus 1.2, 2.4 centimeter. Now, what is the relation between the amplitudes and the intensity? We need to compare the initial, because we have to answer in terms of phi. So I'll be comparing the initial amplitude and the resultant amplitude. So I'm going to call the resultant intensity. I'm going to represent by this symbol. The intensity of the wave x was I and the amplitude was 1.2 centimeter. The resultant intensity has amplitude 2.4. So we need to find the ratio. Okay. The formula that we have is I1 over I2 equals to A1 square over A2 square. Where do we have this formula? The very first chapter of waves, in the subtopic intensity of wave, you'll find this formula. In the very first workbook of waves, I1 over I2 equals to A1 square over A2 square. You can call this one I1. You can call this I2. You can call this one A1. And you can call this A2. Let me insert the values now. So if someone can find me the value of this thing, 2.4 square divided by 1.2 square. Okay, 4. So instead of this thing equals to 4. So I resultant over I equals to 4. We need to find the intensity of resultant in terms of I. Alright, so this one would be 4I. Okay, meanwhile we have a question, sir, why did you take this value of n although it is not mentioned? I suppose you might be referring to the previous part. We took a different value of n because in order to produce the next interference, in order to produce the maxima for a different wavelength, you have to change the value of n. I could have taken the value of n from 3. Instead of 3, I could have taken the value of n to be 1. But if you solve by using the value of n, the wavelength that you get does not fall in the region of wavelength of the visible light. So initial value of n was 2. I could have taken a different one which is 1. I could have taken a different one which is 3. If I do it with the value of n to be 1, the wavelength that I get does not fall in the wavelength region of the visible light. That's why I say you need to memorize the wavelengths from the electromagnetic spectrum, all of those. Okay, then we have the next one. Monochromatic light is incident on a diffraction grating. Okay, monochromatic simply means kind of a laser, a single color. If it is green, it stays green. Describe the diffraction of light as they pass through the grating. A normal one, I mean, we studied the diffraction grating. Matter of fact, we studied by a monochromatic light. So once the waves pass through the diffraction grating, okay, so here we have the next one. A parallel beam of light consists of two wavelengths. This one is pretty much the same question, the one that we did initially. Parallel beam of light consists of two wavelengths, 540 and 630. Okay, so two different wavelengths. The light is incident normally, means uh, the angle theta is given as 90. Third order third order diffraction maxima are produced for each of the two wavelengths. The value of n is 3. No higher orders are produced for either wavelength. So maximum that you get is 3. Determine the smallest possible line spacing d of the diffraction grating. So first of all, ladies and gentlemen, you need to score at least 1 mark from this question, which is to write down the formula n lambda equals to d sine theta. This is the first thing. You write this one, you'll be scoring at least 1 mark, C1, compensation mark for the formula. Now the thing is, I gotta pick a situation. I need to pick out of these two wavelengths which would give me the smallest value of d. I need to pick up a wavelength that would be giving me the smallest value of d. So that thing needs to be picked. What is the situation? Well, the thing is, you can do, if you struggle with it, do it with both the waves. First, find the value of d using the first wavelength, then find the value of d using the second wavelength. This is the standard method. So n lambda equals to d sine theta. I'll make d the subject and d equals to n lambda divided by sine theta. So theta is equals to 90, n equals to 3, and let's say the first wavelength is 540. We'll do it with 540 first, and then we'll do it with 630. We'll do it with both. Okay, so I don't even need to write sine 90 because sine 90 would be 1 anyway. So we need to find the value of d. Okay, smallest possible line spacing. So n is 3. Let me first pick the value of wavelength 540. And then what's the other one? 3 times 630, and you can add the prefix also. But there's one catch here. Only one thing that you need to consider. There is something that we need to consider that was missed initially. The question is, third order diffraction maxima are produced for each of the two wavelengths. And by the way, the question was, determine the smallest possible line spacing d of the diffraction grating. So we found the value of d using the first wavelength, we found the value of d using the second wavelength, and it turns out apparently that the smallest value of d is this one, 1.62 into 10 raised power minus 6 meters, or should I say 1.62 micrometer, and the other one was 1.89 micrometer. So apparently it looks like the smallest value of d is 1.62, but we need to ensure that if we use this value of grating, then the third order maxima should be produced for both of the wavelengths. So the thing is, once again I repeat, this would be our answer if this would be the answer if the third order maxima can be produced for both the wavelengths with this diffraction grating. So how do we know? How do we know, for example, that third order maxima can be produced using this value of diffraction grating? How do we know? We'll try to find the value of n. And if the value of n is 3, it means it can produce the third order diffraction maxima. And at the same time, for both of these wavelengths, the value of n should not exceed 4, because it also reads no higher order produced for either wavelength. So let's check if this can produce third order maxima. This value of diffraction grating can produce third order maxima. So let's use this value and we'll try to find out. I'll paste over here, and the two wavelengths are, by the way, 540 and 630. So here's the first one, 630 nanometer, and the other one is 540 nanometer. So I'm going to see if I use this one as the diffraction grating, and the wave is incident normally, which is given in the question. The wave is incident normally. Incident normally means the angle is 90. We don't have to worry about the angle. So angle is 90. But I'll use the smallest. Let's say this is the smallest value of d. But at the same time, can it produce third order maxima? And also, it should be able to produce third order maxima, and no higher order should be produced in the process with each of the wavelengths. So let's see which order maxima do we get if we use the wavelength 630. And lambda, I'll be writing the formula once again. You see the formula, you keep using it, same formula over and over again. And lambda equals to d sine theta. So I mean sine 90 would be 1. I don't even need to write it. The value of d is 1.62 into 10 to the power minus 6. Lambda would be divided. The first value of lambda is 630 into 10 to the power minus 9. So can somebody do it on the calculator quickly? And let's see which order maxima is produced for this wavelength. It should be able to produce third order, and it should not exceed 4. Then this value of d1 is the smallest diffraction grating. There you go. So we get the value of n as 2.57. Value of n is 2.57. And if you could remember, I told you that in this case, the value of n has to be rounded down. What does that mean? You're getting two maximas, but the third one is not there completely. The third order maxima is not produced completely. Even if the answer were, let's say, 2.99, we would still round it down to 2. We won't say 3 because the third one is not complete. There is 0.01 uh, still missing. Okay, 0.01 is still missing in that. So there is a very, very small percentage still missing. It means if we label this as a minimum value of D, but it is not satisfying the condition, it is not producing the third order maxima. So this cannot be the smallest value of D. Hence, by process of elimination, you don't even need to check for D2. If you want, you can, but you don't even need to check D2 because the first value of D1 is eliminated. Now the only distance possible is 1.89 into 10 raised power minus 6. So although the first value of D1 is smaller, but the problem is it doesn't produce third order maxima with the wavelength of 630. Will it produce the third order maxima with the wavelength 540? Yes, it will. But the question was, it was given in the question that the diffraction should be able to produce third order maxima for each of the two wavelengths. So if it fails at one, it is not the smallest distance. So the very advanced questions, from this topic can look something like this. If you write this value of D, I think you'll be getting 2 marks. I haven't seen the marking scheme though, but the marks distribution, but I think you'll be getting 2 marks. If you're clear with this one, shall we proceed to the next question? So here we have question number 5. In case you were like I remember assigning these questions. But if you're done with those questions already, you can just cross-check the answers. And not only the answer, you can cross-check the method also. So here we have question number. All right. So question number 5. A ripple tank is used to demonstrate the interference of the water waves. Two dippers T1 and T2 produce coherent waves. Coherent means waves which have a same or uniform phase difference and have circular wavefronts as illustrated in figure 5.1. Okay, not a big deal. We saw these kind of waves in simulation also. Once they produce the water waves. The lines in the diagram represents the crust. Okay, so for example, for the source one, this is the crust of the source one. Okay, I mean, let me narrow it down first. Yeah, this is the crust of the source one over here. This is the crust of the this is the second crust of the source one. This is the third crust of the source one. Likewise, this is the fourth one. and then this is a fifth one, and then this is a sixth one. So the lines represent the crust, and the region in between subsequently represent trough. This is the trough of the first source, this is the trough of the second source, this is the trough of the third, this is the trough of the fourth, this is the fifth trough. So same applies for the source D2. Let's see what the question is. So the question is, one condition that is required for an observable interference pattern is that the waves must be coherent. Okay, this has to be memorized as a fact also. Condition of interference. The lines represent in the diagram represent crust. The waves have a wavelength 6 centimeter. Okay, now we know one thing for sure. 0.06 meters is a wavelength. For which one? For D1 or D2? For both. If the waves are coherent, they'll be having same frequency, they'll be having same speed, they'll be having same wavelength, they'll be having same type also. If one of them is water wave, the other one would also be water wave. Describe how the apparatus is arranged to ensure that the waves from the two dippers are coherent. Well, the dippers should be vibrating or should be moving with the same frequency. And how do we ensure that the dipper have the same frequency? The dippers would be connected to the same vibrating machine, to the same vibrator, to the same motor, anything that you want to write. So both dippers you can also call it the motor to the same motor, or you can also call it to the same vibrator, which means the same thing, but you gotta use the vocabulary words or the key terms in physics. Okay, state one other condition that must be satisfied by the waves in order for the interference pattern to be observable. So what we can add is the two waves should also have same amplitude. What would happen with the same amplitude? You will be seeing the destructive interference also. Otherwise, the destructive interference, you won't be able to see the destructive interference. And what do we mean by destructive interference? When the crust of one wave falls on the trough of the other. And in order to get the purely destructive interference, the two amplitudes should be same. So the two waves should be having same amplitude. The reason is, if you want to write it as a side note, the reason for this is, even if the amplitudes are not same, you will get the constructive interference. But for the destructive interference, for the pure destructive interference, the amplitude should be same. Only then, let's say +2 can be cancelled out by -2. And the resultant displacement would be exactly 0 if the two waves have the same amplitude. And then we have, yeah, so far theoretical, no formula up till now. Light from a lamp above the ripple tank shines through the water onto a screen below the tank. Describe one way of seeing the illuminated pattern more clearly. Okay, for this one, we can take pictures of the pattern after regular intervals. The picture can be taken at the regular intervals, and we also have some an instrument which is known as stroboscope. So it is the instrument which emits uh, flashing lights at specific intervals, which are used to capture the snapshots of the pattern. Okay, there we go. Something interesting now. Mathematical. The speed of the waves is this much. Calculate the period of the waves. I think we were provided with the wavelength also. It was, if I'm not wrong, 0.02 meters, aka 2 centimeters. Oh, sorry, my bad. 0.06. 0.06. Calculate the period of the wave. So V equals to lambda divided by T, thereby T equals to lambda divided by V. Lambda is 0.06 and the speed is 0.40. If someone can hit it on the calculator. Okay, Abdul Rafi sir, isn't a black screen used below the tank to see the interference? That can also be used. Yes, that is one of the suggested answer. So what we get is 0.15. So 0.15 seconds. Okay, part D. Figure 5.1 shows a point X that lies on a crust of the wave from D1. Alright, okay. So from D1, it lies on the crust. Okay, from D1, it lies on the crust. And midway between two adjacent crusts of the wave D2, from D2, midway between two adjacent crusts. In other words, on a trough, midway between two adjacent trough means on a trough. So we can even write here to make it easy for us. And on a trough from D2. For the waves at point X, state the path difference in centimeters. Yeah, I should be taking a look at the picture also. Maybe we do have the point X. Oh, okay. Okay, we do have it. So let's start off with D1. First wavelength 2 lambda up till here, and up till here it is 3 times the wavelength. So distance of X from D1 is 0. It is 3 lambda with respect to D1. I'll note it down and then I'll look the difference. Three lambda from with respect to D1. Sorry, with respect to source. Yeah, D1. With respect to source D1, It is at a distance of 3 lambda. Now let's take a look how far the point X is, not from the source D1, rather from the source D2. So lambda, 2 lambda, 3 lambda, 4 lambda, and it is in the middle of third and the fourth lambda. So with respect to D2, it is at a distance of 3.5 lambda. With respect to D2, it is at a distance of 3.5 lambda. Now what is the path difference? Well, we simply insert a negative sign, the greater distance minus the smaller distance, or you can do it the other way around also and then just simply ignore the negative sign. So 3.5, the wavelength was 0.06 minus 3, the wavelength was 0.06, and what do we get? Okay, 0.030, thank you. 0.030, and we got an answer in centimeter. Okay, we can convert it into centimeter. 0. I didn't see that we need to give the answer in centimeter. So in centimeter, it would simply be 3.0. Okay, gotta refrain from writing 3 centimeter. The physical quantities should always be given in at least 2 SF. The physical quantities. All the measurable quantities should be given in at least 2 SF. For some of the answer, for example, the value of n. The value of n could be first order maxima, second order maxima, third order maxima. Those values can be written in 1 SF because those quantities do not have a unit. So technically those are not physical quantities. The physical quantities are the quantities which are measurable and they are measured in a specific unit. N has no unit. So n can be written to 1 SF. Okay, anyway, we need to find the phase difference between these two. The phase difference between the two waves at the point X. So, I mean, the simplest solution is for 1 mark. We don't want to complicate that. This is how many times the wavelength. The difference is 0.5 lambda. So when the path difference is not integral multiple of lambda, the phase difference would be 180. If it is 0.5 times lambda, 180. 1.5 lambda, that to 180. Yeah, just wanted to write down a formula by which you can convert what do we call path difference into phase difference. You can note down the formula also, but this one was kind of easy for 1 mark. But if it is slightly tricky, the values are not so simple, then you got to use a formula. So delta phi, which is the phase difference, equals to delta x over the wavelength times 360. So you can use this formula also. So for example, what was the path difference? It was 3 centimeter divided by, what was the wavelength in centimeter? 6 centimeter times 360. So you would know, like 3 2s are 6, then 360 divided by 2, you'll still be getting 180. But you should note down this formula by which you can convert phase difference into path difference. And to be honest, it is just cross multiplication. It is just the application of cross multiplication. So what you can do is, let's say wavelength here and angle here. For a wavelength of 1 lambda, the angle was 360, and for a distance of delta x, the phase difference would be delta phi. And then you can cross multiply to make delta phi the subject, and you'll be getting this formula. So it is basically cross multiplication, but if you want to memorize it as a formula, you can. On figure 5. This would be the last one. On figure 5.1, draw one line at least 4 centimeter long which joins the points where only maximum of the interference pattern are observed. So maximum would be observed wherever the crust falls on the crust. So for example, yeah, I gotta raise these one for a moment. I see a point straight away over here, crust combining with the crust, crust combining with the crust, crust combining with the crust, crust with the crust, crust with the crust, or could have been otherwise trough combining with the trough. Means the same thing. So I'll take the ruler and I'll connect these points where the crust overlaps crust of D1 overlaps the crust of D2.